because that's the Fischer esterification, and I promised you that on the quiz on Thursday. Actually, so let's apply lever logic here. There are three different kind of fundamental mechanisms, right? Saponification was an example of a negatively charged basic nucleophile attacking an unreactive acid derivative. We just did a bunch of examples of neutral nucleophiles attacking reactive acid derivatives. And now we're going to talk about neutral nucleophiles with unreactive acid derivatives. What's going to be on the quiz?
A little bit of each. Or just one? Are you going to pick just one or all three?
Well, didn't we just have one on today's quiz?
Yeah, but it was your choice.
So we had saponification on today's quiz, and since that was fewer steps than the other one, I'm sure everybody did that one instead of Colby reaction.
I did them both.
So logic would suggest the other two are probably going to be on Thursday's quiz, so that you get the experience of doing all three. So I'm going to use as my example here 1-hexanol and acetic acid. The catalytic concentrated sulfuric. Because that's the reaction that you did for your pre-lab balanced equation and set your pre-lab table up for the unknown alcohol level. Or you will do that this week if you didn't do it already, because this week is group B is doing this reaction. So the problem is that the carboxylic acid is an unreactive acid derivative. So this carbonyl carbon is not going to be attacked by the alcohol oxygen spontaneously. Not a good enough, right? We don't have a good enough electron withdrawing group on here to pull electron density away to make that carbonyl group polarized, and hydroxide is a crap leaving group. You're not going to lose hydroxide in acidic solution, right? That's not going to happen. So what we're going to need to do is activate this carbonyl group by protating it. So what's the proton source?
The catalyst?
Probably the catalyst, right? This is a stronger acid than the conjugate acid of the carboxylate. So logically, the first thing we're going to want to do is protonate that acetic acid. And you're running this in the lab in an excess of acetic acid. You've got, I think, 4.4 protons of acetic acid. So step one is protonation, which makes sense when you're in strong acid. Step one is always going to be a protonation step. And I'm showing the resonance structure that still has the filled octet on carbon and the positive charge on oxygen, because I used a pair of electrons from the oxygen, a lone pair, to do that attack. Now we have a carbonyl group that is reactive enough to be attacked by a neutral nucleophile. And we can apply the great rule of organic chemistry number 1 to understand why. Right? There is a resonance structure that has a positive charge on that carbon. So now our hexanol can attack carbonyl carbon and push a pair of electrons on. Generate that tetrahedral intermediate that you knew had to be coming. So now we need a proton transfer step, because what we need to do is get this hydrogen off of here and onto one of these OH groups so that we can lose water. The the other product of this reaction, we just write out the balanced reaction. Is water. We're going from 1-hexanol and acetic acid to hexyl acetate. 1-hexyl acetate and water. So this hydrogen, this oxygen, and this hydrogen are becoming water. Hydrogen from the alcohol and the OH group from the acetic acid are going to become water. To lose water, we need to have OH2 plus. So we need a proton shuttle, somebody to move that proton around, and the logical proton shuttle to use in this case is acetic acid, because we've got an excess of acetic acid present. We don't have very much sulfuric acid. So even though in that protonation step we're going to be generating the hydrogen sulfate ion, there's not a lot of hydrogen sulfate ion around. It's probably acetic acid that's going to move that proton. So we're going to take that proton off to generate a neutral intermediate. There's 2 OH groups and an O arc. And now we've got protonated acetic acid. The first thing that happens when you took sulfuric acid into acetic acid solvent is sulfuric acid protonates the acetic acid. So now we're going to take the hydrogen off acetic acid. Do another proton transfer step. We've generated a leader group that we didn't have before, and acetic acid back. All right, so we're going to be going back and forth from protonated acetic acid to neutral acetic acid as it moves protons around. Next step is to kick off the leader group. And I've shown it not being pushed by this load pair. I've shown it just falling off and generating a trivalent carbon. But I could have showed that being pushed, because there's a resonance structure that looks like this. And this has a positive charge on the oxygen. To get to here directly, I would have just shown the second arrow going from the OH group. And now I think it's fairly obvious that you just need to take that proton off. Using acetic acid. And that's going to generate this product. And regenerate the protonated acetic acid. Which can either shuttle a proton around or get attacked by another molecule from 1-hexanol. So it's a 6-step mechanism instead of a 3-step mechanism in an acid, because you've got a lot more proton transfers. We still have 1 nucleophilic attack and 1 loss of leaving group in step 2 and step 5, but now we've got 4 proton transfers instead of a single proton transfer. protonate the carbonyl group to generate a more reactive carbonyl. Right? Because we now have a positively charged molecule. Then we attack with a nucleophile. 2 successive proton transfers, basically just getting the proton off the nucleophile and onto the oxygen that's going to act as the leaving group. Then we can lose the leaving group, and then finally a deprotonation to generate the final product. You'll notice I've shown every one of these 6 steps as a equilibrium, which means that we can hydrolyze an ester to the carboxylic acid by treating it with water and catalytic acid. Which direction this lies depends entirely on your ratios of product. If you have a lot of water present, you'll tend to push the reaction towards the alcohol and the carboxylic acid. If you have a lot of alcohol present or a lot of acetic acid, right, we're going to use an excess of one of those reagents to try to push the reaction forward by those catalysts. So in our case, because the alcohols are mostly more expensive than acetic acid in the lab, we're using an excess of acetic acid. But in many cases in the lab, in research, your carboxylic acid is the expensive component and your alcohol is cheap. So what you end up doing is using an excess of the alcohol. So you should be able to do this reaction in reverse as well. You should be able to take an ester and water in the presence of catalytic sulfuric acid, in which case your acid source would become hydronium ion, H3O+, and work all the way backward. Same intermediates, right? We protonate the carbonyl group. We would then use water as a nucleophile to attack, because water is one left in step 5. 2 successive proton transfer steps to get the hydrogen off the water and onto the alcohol, so that the alcohol could act as the leaving group in step 5 of the reverse reaction. So, standard mechanism, I'm going to ask you for this for sure, either forward or backwards. 6 steps, 4 proton transfers, and 1 nucleophilic attack and 1 loss of the leaving group, which are in the second step and the penultimate step. The last step and the first step are proton transfers, and then those 2 middle steps are also proton transfers. This mechanism in this direction is called the Fischer esterification. It's not limited to the formation of esters. You can form amides under acid catalysis. You can hydrolyze amides, you can hydrolyze esters, and you can hydrolyze nitriles, all in aqueous acid to generate the carboxylic acid. Third basic mechanism quiz. Hopefully you can master these 3 different types of mechanisms. Let's talk about hydrolysis of nitriles. The nitrile is a carboxylic acid derivative. So we should be able to take acetonitrile and treat this with aqueous strong acid, heat it up a little bit, and generate the carboxylic acid. But that mechanism is going to be a little different. Because there's going to be a nucleophilic acyl addition mechanism starting, right? Before we can do a nucleophilic acyl substitution. There's no leaving group here. And it requires a leaving group attached to that carbon in order to do the nucleophilic acyl substitution. So the mechanism is going to be more steps. There's actually going to be a nucleophilic acyl addition first. Then there's going to be a telomerization. And then there's going to be nucleophilic acyl substitution. you're going to need 2 molecules of water, and the other product is going to be ammonia. Or in this case, it'll be the ammonium ion. So the net reaction is to take three of the hydrogens from water and the nitrogen here to generate ammonia, and then you're taking the other oxygen from water and the OH group from water to form your carboxylic acid. So, if I were to ask you for the mechanism, and you didn't know it, where would you start? Say you skipped class and you didn't hear, hey, the next quiz is going to be hydrolysis of nitrile and nucleic acid, and you didn't want to just take 0 on the quiz. What would you do?
Can you protonate the nitrogen?
You need to protonate something. And the thing that's logical to protonate because it has a lone pair is the nitrogen. The nitrile is not a good enough electrophile. It's not a reactive enough carbon to react with a neutral nucleophile without activation. So we're going to protonate it. To generate intermediate that looks like that, which is resonance stabilized, right? You can pull a pair of electrons on the nitrogen and have a positive charge on carbon as well. But because that would be less stable, I'm writing it with Philbach text. So what would the second step be? And of course, we generate water in the process. Just took the proton off.
Can you use one of the bonds in the triple bond to attack the water?
This isn't going to attack anything because it's positively charged.
No, the electrophilic.
It's going to get attacked.
Oh, yeah.
So the water lone pair is going to attack the carbon and push a pair of electrons onto the nitrogen to make it neutral. So this looks fairly similar to what you've seen before, where we have protonation followed by a nucleophilic attack. It's basically a nucleophilic acyl addition, right? We're adding the elements of water across that carbon-nitrogen bond. We need to take this hydrogen off. Regenerate our acid catalyst. And what we've generated is kind of like an enol, right? It's not an enol because that's not a carbon-carbon double bond, it's a carbon-nitrogen double bond. But it's a lot like an enol. And we know that enols are unstable. When we have an OH group on a carbon-carbon double bond that's not stable, it's not illogical to make the assumption that this imidinol is also unstable and is likely to rearrange to the carbon-oxygen double bond and a carbon-nitrogen single bond. So this is the nucleophilic acyl addition. We just added the elements of water across the carbon-nitrogen bond, the acid to the nitrogen, and the nucleophilic lone pair from oxygen to carbon. Now we're going to do the tautomerization. And you know how to do a tautomerization. what we're going to do is protonate the nitrogen and then deprotonate the oxygen. So two-step acid catalyzed Telomerization. Kind of making an medium ion, and then we're going to take this hydrogen off in water. And we've just generated an amide. So that was a keto-enol tautomerization, except that it was a carbon-nitrogen double bond instead of a carbon-carbon double bond. So now the problem becomes how to hydrolyze an amide in aqueous acid. Amides can hydrolyze in aqueous acid just the same way as esters can. So once we have the amide, we can figure out how to hydrolyze that amide in the pressure gradient section. And it will probably come as no great surprise to you that the nucleophilic acyl substitution part of this mechanism is going to be 6 steps, involving 4 proton transfers, a nucleophilic attack, and a loss of the leaving group. The leaving group is going to be ammonia. So the first thing we're going to do is protonate our meal. And you'll actually recognize that that's going backwards. That's generating the same intermediate that we had before we took that hydrogen off. I just brought it as a different resonance structure now. We're then going to attack this carbon water. And then what we need is 2 successive proton transfer steps, because we need to get the hydrogen off this oxygen and onto the nitrogen so that ammonia can be kicked out as a leaving group. And after step 3, we have a neutral tetrahedral intermediate. Just like we did with the ester formation. So the hydrolysis of an ester and the hydrolysis of an amide is identical. 6 steps, the reverse of the Fischer esterification mechanism. But to hydrolyze a nitrile, we need to go through the nucleophilic acyl addition first, followed by that tautomerization. Now we need to protonate the nitrogen to turn it into a leaving group. Proton transfer. And now I can use one of the lone pairs on one of my oxygens to push that ammonia out. Or you could just lose ammonia and generate a carbon cation. In this case, the resonance structure I've drawn is the one that has filled on text on everybody, which is the more stable resonance structure. The last step will be proton transfer. Ammonia is a better base than water. So that last step is deprotonation. Generate carboxylic acid and the ammonium ion. So it's actually 10 steps to hydrolyze the nitrile. Because I could have taken this intermediate after step 4 here and just intercepted it and immediately added the nucleophiles. Right? Sorry, it's 9 steps. I didn't really need to deprotonate it to form the amide and then turn around and reprotonate it immediately. Right? Those 2 steps are not really necessary. I could have just intercepted this intermediate here after step 4 and done the last 5 steps of the hydrolysis of the amide. Or you could do the 3 steps explicitly, right? There's a nucleophilic acyl addition, that's 3 steps. There's a protonerization, 2 more steps. And then there's the 6-step acid catalyzed hydrolysis, this time of an amide. If this were an OCH3 group, the mechanism would be identical, except for the leaving group would be methanol. So you should be able to do hydrolysis of any of the acid derivatives under acid catalysis in the presence of water, and you should be able to do the forward reaction, taking the carboxylic acid and the alcohol and generating esters through the Fischer esterification. And then, of course, you should be able to do the mechanism for the reactive acid derivatives reacting with nucleophiles that are neutral. The difference between the acid chloride and the anhydride on the one hand, and the amide and the ester on the other hand, is the acid chloride and the anhydride are reactive enough to directly react with the neutral nucleophile without having to be activated by acid. The amide and the ester are not reactive enough to react with the neutral nucleophile until you protonate them. So it requires a switch to that acid catalyst. That's it. We're right on time according to the clock on the wall. We're a little early compared to the other clock. There.
Wait, that was going slow earlier.
Sorry, no, we're a little late according to my computer clock. We're 2 minutes over according to my computer clock.
Oh.
Questions on this mechanism? I'll leave it up there for a little while.